Good morning, everybody. Thank you very much for coming out on a nice day. It's snow. That might have taken away from all the patio fun, but anyway, thanks for being here. We're very pleased to have a presenter who we'll introduce in a moment. I'll be personalize the luncheon today a little bit, and there's two announcements that I'd like to make. This gentleman over here, he revealed to me that he had a birthday. I'm looking at you, Bernard. What are you looking for? Are you revealing the number?
I don't know.
48. I can't wait. Anyway.
Happy birthday!
You get an extra taco. And secondly as well, there's another gentleman who's here, and it's not even been, 24 hours that he has received his Canadian citizenship. And that's Rene Abreu over here. Hey. Thank you.
Hey. Congratulations.
And more importantly, Rene, how's it going, And I know everyone has received the invitation for today's luncheon and speaker. It was quite extensive. That's because Dr. Jennifer Galloway, off to my left, has certainly accomplished a lot of things. Research scientist, paleontologist with the Geological Survey of Canada for a period of time. We've done undergrad over at Queen's, and more importantly, my alma mater, PhD at Carleton University in Ottawa. So on that alone, it doesn't get better than that. That's the other seat out there. So with that, please join me in welcoming Jennifer for the presentation on the giant mine. I know there's one guest here as well, up here, who actually worked in that mine as well. So that's Martin. All right. Anyway, I'll turn it over to Jennifer, and please welcome Jennifer.
I'm pretty loud, so hopefully you can hear me without the microphone. Thank you for being here. It's my pleasure. Thank you for the invitation. So I'm going to tell you a story today about arsenic contamination at the former giant mine. I used to live in Yellowknife. I worked as an environmental consultant at Boulder Associates, which is now WSP. And I worked on this site as well as other mine sites in Yellowknife. So I'd like to start with a land acknowledgement. We're meeting here today on the traditional territory of the people of the Treaty 7 region, and the city of Calgary is also home to the Métis Nation of Alberta. So this project, really it started in 2007 probably, and it's an amalgamation of numerous different projects with funding from numerous different organizations. It was a really big project. I'm only showing you a portion of it. Most of the funding came from Polar Knowledge Canada, which is a branch of the federal government, the Geological Survey of Canada, my employer, Government of the Northwest Territories, and then in collaboration with a number of different universities. We did do traditional knowledge studies with different Indigenous groups in the region. I'm not going to talk about any of that today, but I just want to acknowledge that that work was done. So I think most people here are familiar with where Yellowknife is. It's on the northern shore of Great Slave Lake in the Northwest Territories. It's home to more or less 20,000 people. That population fluctuates a little bit with different mine operations. So the city of Yellowknife is sitting on the Slave Geological Province that I'm showing here. There you go. And this project was actually looking at Yellowknife. It was looking at Courageous Lake, which is Seabridge property. It used to be Tundra and Salamita. These are abandoned mine sites. And then we were also wanting to look at Hope Bay, which is, at the time it was owned by TMAC Resources, and now it's Agnico. I'm only going to talk about the Yellowknife work today, though. So this is the Yellowknife greenstone belt. North-south trending here, and this is where all of the gold is in this region. There were two major mines, Giant Mine and Con Mine, but there was a number of other mines in there, notably Discovery, Burwash Mine. I just want to acknowledge that there was quite a bit of mining happening there at the time. And this area, it remains highly prospective for gold, so the company that's in there right now is Goldterra. So Yellowknife has a long history of mining. So claims were first staked in 1935. As I mentioned, several gold mines operated. Giant Mine was the largest. This operated from 1948 to 2004 and produced 7 million troy ounces of gold. There were various owners. Ultimately, in 1999, it was Royal Oak Mines. They went bankrupt, and the government of Canada, then Diane Bynack, now Steernack, Crown and Indigenous and Northern Affairs Canada, took over ownership and remediation of the site. So that is, the cleanup of this site is estimated at about $1 billion. That's just the cleanup part, that's not any compensation. And shown here, this is the head frame from Con Mine, that's no longer there. It was taken down probably about 10 years ago. So the reason Giant Mine has created such an environmental legacy is that the gold was associated with arsenopyrite. It needed to be roasted at high temperature to release gold to make it amenable to cyanidation. What happened when this process first began is there was zero environmental emissions or environmental controls on the emissions. So when the ore was roasted, it produced a volatile gas phase that condensed into arsenic trioxide. This is one of the most toxic and bioaccessible forms of arsenic, and that was released directly to the atmosphere with no emission controls whatsoever. People knew there was an issue, people living in the area, people working in the area knew there was an issue, and eventually a bag house, they just captured it in a bag. And they backfilled the stopes at Giant Mine with the arsenic trioxide dust they did capture. But in total, about 24 million kilograms of arsenic was released in the stack emissions, and most of this was prior to 1963 when the bag house was installed. So the site is now under ownership of Steernack. I already mentioned remediation is estimated about $1 billion, and the long-term storage of the arsenic trioxide that was captured is backfilled in stopes, and they have put in thermal siphons to keep that frozen. That is what the containment method is for now for perpetuity. And you can no longer access the site underground. It is completely closed off now. So aside from the arsenic trioxide, the site's about 950 hectares in size. It has 8 open pits. These contain 60 million tons of tailings, and the arsenic concentration in those tailings is about 1,000 to 4,500 ppm. I'm going to show you some lake sediments that have higher concentrations than this here in the top. The head frame and the roaster stack have now been taken down. There's the former roaster stack right there. And there's the head frame. So these are now gone. So the research we started was to ask the question, what happened to all the arsenic that was released into the atmosphere? How will climate change affect the fate and mobility of that arsenic? And I'll explain why that's important in a minute. And then how do we establish what background arsenic concentration should be for a remediation target in this contaminated region? That question wasn't very easy to solve. So as I mentioned, the area remains highly prospective for gold. So Goldterra is working in the area. They have properties north of Giant Mine. And we've worked in collaboration with them, so they're very interested to determine precisely what the contamination signal is from giant mine, for obvious reasons, on their property. And I also want to acknowledge the environmental justice aspect of this. I'm not going to get into this very much, but I did want to draw to your attention. There's a movie that's been made about this with the Yellowknife First Nation. And the Yellowknife First Nation also has a petition to address the environmental injustice of what happened here. So, a little background about arsenic and why it's toxic. It's naturally occurring with many minerals, mostly sulfur. Acute exposure interferes with cellular metabolism, and chronic exposure is carcinogenic. This is what arsenic trioxide looks like right here. It is the oxidation product of arsenic sulphides, and it rarely occurs naturally. So the only natural known occurrences of this are from mine fires, coal seam fires, and in some hydrothermal systems. I had a video here, there it is. I don't know if I can make that play or not. I'll explain it. So arsenic occurs in two oxidation states in the natural environment. That's arsenic 5, which is in the oxygenated state. Arsenic 5 will usually sorbed onto the surface of iron and manganese oxide in shallow oxidizing sediment. When this is produced, arsenic 3 is generated, and this will desorb from those surfaces, and it will either move up into the pore water and into the water, or it'll be incorporated in reducing sediments in the formation of sulfide minerals like pyrite. So it can go either way. So the reason this makes arsenic so susceptible to climate change is because with increased primary productivity or increased input of organic matter into the water, it'll drive latent conditions to reducing. So it'll drive the system to be producing more arsenic 3, which can go either way, up into the pore water or down into the sediments. And climate change, we know is happening at unprecedented rates. It is particularly severe in high northern latitudes. We don't need to wait for the predictions of 2 to 3 degrees Celsius warming for the cryosphere to be affected. So that will happen at the temperature melting, so about 0 to 2 degrees. And at that point, hydrological and organic carbon cycle will undergo massive change, and that is what's going to be affecting these lake systems and then the arsenic. So to tackle the first research question, how do we determine geochemical background? So when I worked at Boulder and I was working on these sites, the remediation targets were set at 150 part per million arsenic, so that's well above Canadian Council Minister of Environment guidelines of 17 ppm for probable effect level on aquatic life. Where did this number come from? I was asking that question. The idea was that this is naturally mineralized region, so the arsenic concentration will be higher, and I'll show you that is true, but it wasn't quite 150 ppm. So the previous work on this was primarily focused on areas of known discharge. So this is one mine, and this is the discharge pathway. So the work was focused there, and that makes sense, but that's not background. And then people also looked at soil levels in the Conline trailer park, so people live just here next to Conline. And that makes sense, people are living there, but that's not likely to be background, it's right next to Conline. Some work by my colleague Heather Jameson at Queen's University, and her students took a sediment core from Acacia Bay. So here's Yellowknife, there's Giant Mine, there's Pond. This is Acacia Bay. This was the control site for all of the environmental monitoring at these 2 mine sites. So in 2010, they showed that this site was affected by Giant Mine. So they showed that because this is the sediment core here, and you can see the high arsenic up to 65 ppm. So it increases from 10 ppm, that was probably background, to 65. Then it declines, and this is the same time as, or close to the same time that Giant Mine opened. And then it's high at the top because of post-diagenic mobility, and that's that redox cycling that I was showing you before. So in 2010, they showed unequivocally, in my opinion, that Acacia Bay was not a proper control site, yet it continued to be used as such. So this is a compilation of all of the previous work that had been done to date. Here's what Yellowknife, this is the GMWT background of 160 part per million. These are known impact sites in blue, so these are things like Baker Pond and outlet of Baker Creek. These are known effluent discharge areas. They are known contaminated sites. These are soil outside the city limits, lake sediments. There was only 25 samples at a time. And then this is bedrock down here. So different types of bedrock. So that's what we had to work with. So what we did is we did a lake sediment survey. We sampled near surface sediments of 211 lakes. Here's the city of Yellowknife. So we sampled around here in the western interior platform, south down the Hay River. We sampled intensively around Yellowknife and out the Ingram Trail, which heads to the east, and then all along the tip to Contoito Winter Road. So we sampled there because we could drive there in the winter, and we had summer to operate a helicopter out of using the winter road camps. So we divided those sites into different regions with a real view of looking at the bedrock geology. So those different regions were the western interior platforms, that's carbonate bedrock. We don't expect arsenic to be very high. All along the Tibbet to Contoito Winter Road, this is the slave craton, it's mostly shield. There are pockets of it that are highly mineralized. And then Yellowknife and the Ingram Trail. So I'll show you the results in the next slide, and they're broken down into those different regions. So here's Ingram Trail data, Tibbet to Contoito Winter Road, and these are total arsenic concentrations in ppm. WIP is the Western Interior Province, and then here's Yellowknife data. I'm going to get to that. These are known non-impacted sites and known impact. So I took this here is scaled differently so that you can actually see the differences. So here's median arsenic concentration, minimum, maximum, and then the sample size of all the other sites. So Yellowknife lake sediment samples contain arsenic of over 10,000 part per million. So that was the detection limit of the ICP-MS instrument we were using. Another group went in afterwards and determined that number was 30,000 part per million arsenic. So there's no way that that is naturally occurring in the background. And the other sites had generally between 1 and 25 part per million arsenic, including mineralized areas along the Tibbet to Contoito Winter Road, and including mineralized areas along the Ingram Trail. So if we put those data, which is yellow here, so Tibbet to Contoito Winter Road, Ingram Trail, Western Interior Platform, and now Yellowknife, we moved the Yellowknife background concentration from 160 part per million to 25 part per million. Now, that's a generalization. If you were looking at a lake that was sitting right on top of a mineralized zone, the arsenic concentrations would be higher than that. So that's a median. But we had to take a closer look. So these are just numbers. We had to prove that this was from actual mining and at Giant Mine. Con Mine did roast a little bit of arsenic, but gold ore, but most of it was from Giant. So we had to ask the question, was the high sediment arsenic concentration due to mining or mineralization? So we did a spatial survey. We took our spatial survey data from Yellowknife and we looked at it from every different angle that we could. We did principal components analysis, we did different types of correlations, and what we found is that direction from the historic roaster was the number 2 control in arsenic concentration in these lake sediments, with higher concentrations, these are color-coded, downwind of the former Giant Mine roaster. And then we found that distance was the number 1 control on arsenic concentration, irrespective of bedrock type, with decreasing arsenic concentrations, with increasing distance from the former roaster. So most of the highest arsenic concentrations are on granitoid bedrock, these bedrock have concentrations of arsenic of 2 part per million, so it's not a geogenic source. We also delineated a 30-kilometer radius as the zone of immediate impact from the former giant mine. So with Heather Jameson and her group at Queen's University, they conducted mineralogy on the arsenic in the lake sediments. So we selected, for this work, we selected 8 lake sediment samples from around the former giant mine, so they're all shown here. There's the former mine, there's the city of Yellowknife. And in 5 of those lakes, she was able to identify arsenic trioxide. And if you remember, I told you at the beginning that that's not naturally occurring, that is from roasting at the former giant mine. So this was the first definitive, unambiguous evidence that that arsenic was released into the atmosphere and it persists today in the lake sediments, nearly 50 years after it was released. And then subsequently, her former students, Chris Hsu and Martin Vandenberg, looked at more lake sediments, and they also found arsenic trioxide in Long Lake. This is the beach. This is where everyone swims in Yellowknife. And in Martin Lake, both of these students looked at Martin Lake, and arsenic trioxide is located there as well, and that's an important fishery lake. So there's reasons why they chose to look at these lakes. They're important for people in the communities. Okay, so arsenic is in the sediment, but it is also in the water. So when we did our lake sediment survey, we also took surface water samples. And we found that there was a high correlation between sedimentary arsenic concentration and surface water arsenic concentration. So that means it is moving between the sediment and the water. And Mike Palmer, my colleague, who's at Warwick College now, he's worked for the government of the Northwest Territories. He led the surface water work. And this is the map that was released by the GNWT. Again, you can see this hotspot downwind. This is surface water arsenic data. And the same radius of a hotspot, so about 30 kilometers distance. And the government of the Northwest Territories released a public health advisory based on this data. What they did is they color-coded the different lakes and then identified which activities were safe and which activities were not safe around that area. So people that live in Yellowknife, it's really common to just drink the water. They don't have to worry about giardia. A lot of people harvest berries, mushrooms, fish, and other game around these lakes. A lot of people have cabins on these lakes. Okay, so we know there's high arsenic in the sediment, we know there's high arsenic in the waters, we know which lakes have that contamination signal. And we wanted to now explore the climate change question. So what will happen with warming climate? What will happen to this arsenic? So we wanted to look at what is affecting arsenic in the sediments. I've already told you its distance and direction, but what else? So we did meta-analysis, and what we found is that it was different types of organic matter. So we have the HAWK, or the Rocky Bell 6 pyrolysis machines at the GSC. Anyone that's familiar with the hydrocarbon industry, this is a routine screening tool. But we're starting to use it a lot more in environmental geology because we can characterize different types of organic matter that are relevant for the mobility of toxic trace elements. So we found that S1, this is labile, this would be hydrocarbons if you're looking at hydrocarbon assessment, that's the free hydrocarbon. In shallow sediments, what that is labile organic matter. So it's the insides of algae, basically, but it's highly reactive because it's not very degraded. So why would S1 carbon or labile carbon and arsenic have a relationship? That would be expected for things like mercury. For arsenic, we know it moves with dissolved organic carbon, but no one had ever really looked at its role as solid organic carbon before. So this is work from Chris Hsu that I showed you previously. These are different analyses of arsenic-bearing minerals in Yellowknife Lake sediments from Martin Lake and Long Lake. And this is probably what the most important part is. So this is rhamboidopyrite that forms in shallow sediments from early diagenesis. It's authigenically precipitated. but it's microbially mediated. So that S1 carbon is probably fuel for these microbes, and arsenic is incorporated into this mineral in the shallow sediments in reducing conditions. So just to reiterate that point further, we also looked at the relationship between S1 and sulfur, and arsenic and sulfur, because pyrite is iron sulfide. So that's just more evidence to support this hypothesis. And this is what that stuff looks like, that S1. So this is under fluorescent microscope. It's the highly fluorescing algal cell walls and intracellular soluble organic matter. This is from Martin Vandenberg's thesis and paper, as a student of Heather Jamieson's that I showed you previously. And this is what we think is happening here. So there's input of arsenic. It could come from rocks, like from mineralization. We know it came from the roaster. Arsenic trioxide is not dissolving in the lake sediments, despite the fact that we know it's highly bioaccessible and easily degraded, but it is still there. And this may release arsenic in reducing conditions that could be incorporated then into the arsenic sulphides in the process I just showed you, and then buried in sediment. Or it is released into the pore water. And I'm going to show you that portion in the next slide. So the arsenic can go into the sediment. It either gets incorporated into sulfides and is buried, or it is released into the pore water. And it is the oxygen or lack of conditions that drive that system either way. So my colleague Mike Palmer looked in detail at some small lakes in the Yellowknife region, and he wanted to know, why does arsenic persist in these lakes in 50 years? Why isn't it just all being buried in the sediment and sequestered, and that's the end of the story? What he found is that in the shallow lakes that become reducing under ice in winter, that is driving the perpetual release of that arsenic. It is just cycling year after year after year after year. So it's going into the waters in the winter. When it's reducing, then it will go into the sediments in the summer when it's oxidized. And it just keeps going like that. And the more shallow the lake is, the more susceptible it is to those under ice reducing conditions. Those lakes are the ones that are where the arsenic is not being attenuated at all. So I just want to touch quickly on exploring the climate change question a little bit more, because we can go back in time using lake sediment cores. So lake sediments accumulate annually. We can go back in time hundreds to thousands of years, if not longer, to examine the different climate states and then to examine how that was related to chemistry in lake sediments. So we looked at Pocket Lake. I'm going to describe that in a moment. But here's the type of resolution that you can get, and here's the type of freeze. This is the type of coring we typically use. It's a frozen triangle shoved into the sediments. And the reason we want to use this instead of open tube coring is because even just a millimeter of sediment can be decades to 100 years of accumulation, because the sedimentation rate is so slow in these northern lakes. So then we take those frozen cores and we slice them using a sludge microtome. This was actually something that was used to produce thin sections of plants, and now we just apply it to these lake sediment cores. So we can get really thin slices of material. And then we take those sediment samples and we further subdivide it to look at different things. So this is my expertise is pollen. Some people might look at diatoms, chironomids. These are the head capsules of midges. And we use these to reconstruct climate. And then we can look at the organic matter characterization and then the elements and put it all together. So I'll show you an example from Pocket Lake. So Pocket Lake is located right here. So here's Giant Mine. These are the tailings ponds. And here's another image of it. So Pocket Lake is the lake where the 30,000 part per million measurement came from. So we know this site is contaminated. It's also sitting right on top of the mineralization that was being mined at Giant. So it has two sources of arsenic. So it was a really interesting site to go back in time before there was any mining and find out what was the arsenic in a site that's sitting right on a mineralized zone. So we cored Pocket Lake in 2012 using the freeze core. We dated it using lead-210 and radiocarbon and here's our H-depth model. And then here's the geochemistry. So we did a full element scan, but I'm only showing you antimony because it's not very mobile, and arsenic. And the core goes back to about 3,500 years BP. This is a warm time. It's called the Holocene hypsothermal. So temperatures were about 2 degrees warmer than they are today. Then we entered a neoglacial interval. So we had a reactivation of glaciers in the mountains in North America. Then we had the medieval warm period. This is when the Vikings left Scandinavia and went to Iceland and Canada. And then we have the Little Ice Age, and then finally at the top warming. So we have a really good paleoclimate record for this interval. Now what we find with arsenic, now this is a log scale. Okay, so 10,000 parts per million here and 0 here. And what we find for arsenic is it's going up to close to almost 1,000 ppm naturally, 3,500 years BP. This is before there was any money. So we can show that arsenic can be very high and in certain sites where there is a geogenic source. And then it declines with the cold interval down to about 100 part per mil. So these changes are order of magnitude just from climate variability, and we're only talking 2 to 3 degrees Celsius difference. And then it increases at the top. This is the mining signal. So we can show that even a slight temperature change can drive really large changes in the geochemistry of systems naturally. So I'll wrap it up here. I have 2 more slides about the human health impact because a lot of people have questions about that. The main conclusions are that we proved that legacy mineral processing at Giant Mine released arsenic trioxide and that it persists in the environment. We established a zone of immediate impact, and we established new benchmarks for remediation. We showed that organic matter affects arsenic in the sediment now and into the future. Lake sediments show that our climate can affect total arsenic concentration by orders of magnitude. So since all of this work was done, there's been a human health assessment. So a group from the University of Ottawa went to Yellowknife and asked people to give them urine samples, toenail clippings, and hair. And they looked at arsenic concentration in those different media. They sampled quite a number of children as well as adults. They sampled people that were living in a DLO, so this is Yellowknife's Dene First Nation community, and those people are living very close to the mine, and they are still participating in traditional lifestyles, so harvesting berries, drinking lake water. And then they sampled other people living in Yellowknife that didn't have that lifestyle. So what they found is that children have higher arsenic.
Attention please, would Miss May Haraya, your access Calgary is here. May Haraya, your access Calgary is here.
They found that some of the arsenic concentration was higher than what they established as biomonitoring equivalents. It's a health risk assessment. But they found that this was due to eating market fish and rice from the grocery store, in addition to drinking lake water. And that for adults eating mushrooms and berries was associated with higher arsenic concentration in urine. Okay, so there's higher arsenic concentration, but what GNWT determined is that the risk to developing cancer from these exposures is about just ever so slightly higher than 1 in 100,000, and that risk would be equivalent to having an X-ray or a CT scan. So that is what they concluded. And yes, with that, any questions? Thank you. Yes?
Yes, I've got a question. It wasn't clear to me at the beginning. You stated it cost about $1 billion to cure the issue, so to speak. Is that being done, or is that just on the shelf?
There is no remediation off-lease. So all of the remediation is only within the lease area. It is being done. So they had backfilled the stoves, they're freezing them with arsenic trioxide and then freezing them, but they're cleaning up the tails. And some of these tails I didn't show you here, before they established tailing ponds, they actually discharged tails right into Great Slave Lake. And so there's a pile of tailings in Yellowknife Bay, and they are talking about remediating those. Whether it's dredging or capping it with concrete is the two things that I've heard. So that $1 billion estimate, that money, to the best of my knowledge, has not been spent. That's what's projected.
I guess my question is partly political in the sense that if you did nothing, would not be better uses for $1 billion of the local community?
I guess it depends how you want to use the land or the water, ultimately, yeah. Yes?
I had a question, one of your last graphs, showing the time back to 3,500 BP, and you had antimony, right?
Yeah.
Was that, those were in parallel basically, and was that just to show that there was no influence of like arsenic trioxide going down, like kind of going into the sediment?
Yes.
Into the profile?
Yes.
Okay.
Yeah, so we wanted to show that the changes in arsenic concentration weren't being driven by post-depositional mobility.
Okay.
Because antimony is far less susceptible to that. Okay, yes?
Was there any other type of associated degradation environmentally around the roaster, like in Sudbury and Flint Pond, we were talking about that there's kind of a dead zone because it's built up with all kinds of toxic elements. Is that the sort of thing that's found here as well?
Yes.
The picture doesn't look terrible, but it's quite northerly.
All the granitoid bedrock is denuded from the sulfur dioxide emissions. So that it's just, there's nothing growing on it, there's no lichen, there's no moss. And you can see that zone to the northwest of the roaster stack still today.
And what sort of scale?
Probably that 30-kilometer radius. If I mean, that's just me remembering, like, I haven't measured that.
Okay.
Yeah, and some concentrations of other elements like cadmium are elevated, but to date, most of the research has been done on arsenic.
Yeah.
Jennifer, I found your data from that core fascinating, going back, how, 5,000 years or so, wasn't it? Something like that?
3,500.
And the numbers are all over the place until you got in the last 50 years or so when it really kicked off. So however can you come up with an acceptable background number for arsenic when you've actually got this data that is all over the place?
I think that's a great question. So baseline or background remediation targets need to be a range. It should not just be one number.
Yep.
It should be a range, and it should be a range that takes into consideration what the next 10, 20, 30 years or whatever the mine life might be, what the temperature might, how it might change in that time. Yeah.
Yeah, we've got exactly the same with selenium coming from BC into Washington. And it's exactly the same, there's a range. And but we hear numbers as though it's going to kill you, but there's actually a range which is completely natural, right?
Yes. Yes, in different climate states. Yeah, sorry, question?
Well, I have a couple questions, but I guess one of the things, how would the new miner deal with this issue going forward?
Yeah, so Goldterra was interested, we collaborated extensively with Goldterra in this work, and we poured a number of sites on their property. So they were interested for two reasons. One, for their exploration data, they wanted to make sure if they were seeing high arsenic as a pathogen, that it wasn't a minor element, that it wasn't just from the mine. And second, they wanted to establish solid background conditions for their site for their remediation targets. So we sampled probably 5 lake sediment cores and maybe 5 lakes in their property. So they haven't started production yet. They're still.
They'll deal with an extraction process that's similar, will they?
They will ship it. So there's
Oh,
no
the-
more
oh.
roasting happening there.
Oh, okay, that's what.
Yeah. You have a question here?
Yeah, in the medieval warming period, there was a weird spike of antimony, and I was just wondering if you knew where that came from.
I don't know a whole lot about antimony. My guess is it's weathering from a mineralized source at that time. So when it's warmer, there's more ice-free season and intensified chemical and physical weathering. What is not at all accounted for is groundwater here. So some of that might be from intensified weathering of exposed antimony-bearing minerals.
And one other quick question, when it comes to like legal liability, if you're like a new mine operator looking to do something in a region that has had historic mines, like how do you navigate that process of like trying to select a site that's been previously used that has contamination?
Well, yes, that's a good question. It was similar to the other question that you had. And we're also working with 2 other gold companies that are mining on contaminated sites. They are not legally obligated to prove that their control site is adequate or what background might be. These are all mandated legalities that come from either the territory or the federal government. But what a lot of these mines are doing are supporting us to do lake sediment coring, and it's above and beyond any legislation. You had a question at the back there again?
I did, but it was answered, it was actually on new mining.
Okay.
I presume the technologies have actually changed in the last few decades. So I mean, if they were to do smelting on site or further production, processing, is the technology now available to prevent this?
I don't know. I don't know the answers to that question. Yep.
You mentioned that potentially there's $1 billion to clean this place up. What is being done right now to clean it up, and who's paying for it?
We are, all of us.
Okay.
We are paying for it, taxpayers.
The reason I'm asking is 15 years ago I ran into a situation. I worked in Faro for a little while, and the environmental arm of what used to be Denison, and it was a Denison company that had the Faro pit last. We, as taxpayers, are paying $30 million a year into perpetuity.
Yep,
Sounds familiar?
yep,
Okay.
yep, sorry, yep.
So I'm curious, for the word perpetuity, there's a deep fridge down there, HVAC or ice arena type, drilled down, frozen. Is there, all these new smart folks, is there any ability, like in the oil sands, I think sediments are finding other, and Lily does it, rare earth elements, critical minerals. Is there any reprocessing or potential to do anything to, I don't know, you have all the chemical, the periodic table up there, but is there any sort of, is it just frozen, so to speak, in time down there?
It is, and it is.
It's like a fridge down there, is that what it is?
The idea at first was that it would be forever, because
Okay.
the permafrost would be stable, and now maybe it won't be, so that hence the thermosiphons.
Okay.
And accessing it is completely closed off. When I was underground in that site, probably less than 10 years ago, I had the impression it wasn't even fully mapped. Where
Huh.
these stopes are,
Right.
it's not really, I don't know that it would be feasible to go in there and
Well,
take this out.
I mean, technology-wise, I work gold mining in northern Saskatchewan, north of Lac-La-Roche, but there's Cigar Lake and all this high uranium, they use robotics, right? So you could probably do robotics down there, do whatever you need to do.
Yeah.
Yeah, okay.
Mike?
Do you have an idea what the giant mine paid in royalties to the government?
I don't know. No.
Should know.
Should never been mine, should have offset one for the.
Oh, yes?
So, I think of the giant and the con mines as kind of being the poster localities for arsenic contamination. But it's not the only ore deposit that's associated with arsenic pyrite. There are many gold deposits around the world. And I think there's some in southwest England as well, famous pictures of barrel loads of white, I think it's arsenic trioxide. And so what's so special about Yellowknife compared to these other localities around the world in terms of this contamination?
I think it's the severity of it and the fact that it was released with no emissions to the atmosphere for so long.
So how would arsenic be handled in other places?
I'm not sure. Yeah, probably, well, when they did establish the baghouse, and there was a number of other emission controls that became increasingly more efficient, my suspicion is that those would have been used at other sites.
Okay.
Yeah. Yes, Sir Renee?
Thanks for your presentation. Appreciate it. This is not related strictly to the presentation, but can you explain me a little bit about the picture that you're showing on the screen? Is that artificial intelligence generated, or is from the space, or why is it there?
No, this is my friend Paul Vesky. He's a fish biologist. I go to the Toledo government, and he took this photo of Baker Creek. So what happened a number of years ago is Baker Creek had an ice dam. So Baker Creek is a contaminated site. And this is a photo of the ice dam, and the ice dam caused Baker Creek to overflow into other lakes. And when it overflowed, it took the arsenic with it in the water. So that's what this is that is what this photo is of. The ice dam and the overflow.
Okay.
Yeah. Yes.
So, thinking about your chart of the antimony and the arsenic, you went back, what, 3,500 years?
Yeah.
Was there a reason that you stopped there? Is that just how long your core was?
That's how long our core was, yes.
And is it at all worthwhile going back further to try and get a better baseline for that area?
It would be a good idea to go back further. So the challenge with the freeze cores, so the longest, what happens is they get stuck.
Okay.
And I've had to use like a front end loader to pop them out before, and this is not feasible at this site. So if we had one that was say 2 meters long, I don't know that we would be able to get it out. There are other coring methods we could use. So you can use Livingston cores, which you can get meters of sediment, and I think it would be worthwhile to go back and have another look. Yeah. Yes.
It might be a two-part question. So there's like mineralogical certainty that the arsenic trioxide is there
Yes.
in the sediment, and we know the mass of the amount that was put into the atmosphere. Like, given that it stays there and it either cycles up or turns into pyrite, what's its residency time? How long? Is there any prediction of how long that kind of freeze thaw cycling will happen going forward?
In the shallow lakes, where this is happening in perpetuity, it's been happening for 50 years. As the climate becomes warmer and it drives even deeper lakes towards under ice and anoxia, new lakes will be affected, and those lakes that are already affected, they will have under ice and anoxia. It might be more severe. Now that could be offset by the fact that the ice on season might become shorter. So, yeah, but the idea right now is that this will continue to happen basically forever.
And it'll just move to a different lake, it just moves down the system.
If it moves to a different system that's connected and that system doesn't have the same redox profile, then it will have different behavior in that system. So these lakes are, the lake that I was sort of highlighting here, I mean, my colleague looked at lakes of different depth and different area, different connectivity. The worst ones are isolated and shallow. Yeah. You had a question?
I did, thank you, Jared. Great presentation. 5 questions back.
Okay.
You indicated that there was no underground mapping of the stores.
I had the impression from Sierra.
When I worked there, we had hand-drawn large maps of every stove at every level.
Oh, I imagine you must have.
And I'm just curious what would have happened to that.
I don't know, and I also don't know why there hadn't been geophysical work done. Now, that being said, I was underground once on one day, and I remember they took us to the end of a stope, and I couldn't tell you, no idea. and they dropped a rock off the side, and it took a shockingly long time before I figured it out. And I asked, how
You mean
deep?
down the shaft?
Yes, and I asked, how deep is it? And they didn't seem to know, so that was my impression.
Okay.
Yeah, obviously it was known by the people mining, they must have,
Right.
yes.
If there's anything else, but Jennifer, if you have a few minutes, you can stay around and handle one-on-ones.
Yes, absolutely, yeah, thank
With
you,
that,
everyone.